I'll tell you when we can start. Then just muted, and then when we go live, 1 minute here, 1 minute here also. Presentation. I know it's recorded. Presentation. Oh, it's live. We can start now. It's live.
Agora onde que eu já estou no ar,
Yes.
né? Bom, I want to present. Estou no ar. We are in the air now. Hoje nós vamos a começar o seminário, o minicurso do professor Porperieschi. O minicurso é síntese e estrutura de chalcones análogos. A primeira parte do minicurso é essa parte. O professor Porperieschi é professor titular da Universidade de Pécs, na Hungria, com quem eu tenho colaboração faz 6 anos. Faz 6 anos que eu colaboro com ele, no qual 2 alunos meus de doutorado fizeram estágio sanduíche, e eu fiz um estágio de pós-doutorado durante 1 ano nessa universidade. Então vamos começar nossa apresentação. Eu já apresentei o professor Paul, e agora eu vou passar a palavra para o professor Paul para começar a sua apresentação. Então aqui eu tenho que colocar ele no estudo.
Yes. And also his presentation. Is that okay? So now you hear and also unmute. You can start when you right now.
You can have it.
So welcome to everybody. I do thank you very much. I do appreciate my invitation from the leadership of the Federal University of Bouyas, and in particular to Professor Caridad. And as she already mentioned, my 2 days lecture is a series of lectures are about the synthesis, stereochemistry, biological functions, and reactivity of chalcones. So let's start with some introduction of myself. I'm from Europe, Central Europe, and from Pécs. Pécs is a small university town in the southwest part of Hungary. Our university is already 650 years old, which is one of the oldest university in the continental Europe. And I'm from the Department of Pharmaceutical Chemistry. Briefly about myself, I graduated as a pharmacist and from St. György University of Szeged. After movement from Szeged University to University of Pécs, I served as a head of department of the Institute of Pharmaceutical Chemistry, and for 3 years, I also served the Faculty of Pharmacy as a dean of it. Besides my university deeds, I also serve the Journal of Pharmaceutical and Biopharmaceutical Research journal as an editor-chief of it. And briefly about chalcones, the topic of this series of lectures. Chalcones are natural products, are intermediates of the flavonoid biosynthesis. As you can see, these molecules are practically constructed from three separate, and of course, linked units, two aromatic rings, ring A and ring B, plus an enone linker, and as a whole, it takes a conjugated system. In natural chalcones, both the A and the B rings have several substituents. Most of them are hydroxyl groups and methoxy group. Because of the wide range of pharmacological, biological activities of chalcones, a large number of synthetic analogs of chalcones have also been synthesized, and these natural and synthetic chalcones also show a variety of different reactions. These reactivities can be used to synthesize new organic compounds. Most of them are heterocyclic derivatives. However, these reactions can serve as a basis of molecular action of the chalcones, biological actions of chalcones, and that's why I wish to start my lecture in a short introduction of these reactions. As a conjugated system with a polar carbon-carbon double bond, chalcones can ready to react with the nucleophilic reagents in a Michael type reaction to create a duct, and the nucleophile is linked to the beta carbon. Concerning the stereochemistry of the carbon-carbon double bond, there are two different isomers of the molecules, with mainly those ones in which the carbon-carbon double bond has got E configuration, and the other one in which the carbon-carbon double bond has got Z configuration. In both configurations, it's shown in the slide. The configuration, the sigma bond between the carbonyl and the carbon-carbon double bond is S-cis. Another important reaction of the molecules in the hydroxylated compounds derivatives in particular are the radical scavenging activity, which is important both in biological in vivo systems and in non-biological in vitro systems. Furthermore, in the presence of proper oxidizing agents and proper substitution of the aromatic rings R1 and R2, oxidation could happen at both rings. The main biological effects of chalcones can be summarized in according to the following schemes. One of the biological effects this series of lecture will also talk about is the so-called cytotoxic effects, which are selective towards the carcinogenic cells. The mechanisms of this cytotoxic effects includes induction of apoptosis, anti-mitotic effects, and mitochondrial uncoupling. The other characteristic and important biological effects of chalcones is their chemopreventive effects. The chemopreventive effects are manifested through induction of apoptosis, through antioxidant effects, and modification of activities of phase 1 and phase 2 enzymes. For example, inhibition of cytochrome P450 enzymes, which are involved in generation of electrophilic intermediates, induction of NADPH dependent quinone reductase, which are involved in eliminating electrophilic quinone derivatives, inhibition of the aromatase enzymes, inhibition of angiogenesis, and in some particular cases, inhibition of formation of nitrogen monoxide. Besides these two characteristics effects of chalcones, we also should mention the antibacterial, the antifungal, the antiviral, and the antiprotozoan effects. Among them, the antibacterial, the antifungal, and the antiprotozoan effects are very well documented in the literature. As for the in vivo antioxidant effects, there are several different mechanisms through which these antioxidant effects of chalcones are manifested. In this series of lectures, we will show some details on the radical scavenging effects of the molecules. In the first part of the lecture, I'm talking about briefly summarize the different synthetic methods which are used to synthesis natural and non-natural derivatives of chalcones. Among them, first I should mention the so-called Gleisenschmidt condensation, which is the most common pathway, most common method to synthesize chalcones and chalcone analogs. The Gleisenschmidt condensation involves a reaction of an active methylene compound and the aldehyde. In case of chalcones, which is and the example, which is acetophenone and substituted benzaldehyde. The reaction can be managed using acid or base catalysis. In case of base catalysis, the base deprotonate the labile hydrogen atoms next to the carbonyl, and it's the analyte intermediate which attack the positively polarized carbonyl carbon atom, resulting in formation of the aldol intermediate, which can undergo dehydration, elimination of water, resulting the expected aldol condensation. And in another way, the reaction is performed by means of acid catalysis. In that case, anol is also formed, which reacts with the protonated carbonyl, and the protonated carbonyl, whose polarity is increased due to the protonated carbonyl oxygen, is reactive enough to react with the inward form of the reactant to form the aldol adduct, which, similar to the previous pathways, results in the expected enone derivatives through elimination reactions. As for the stereochemistry of the products, the main product, which typically crystallizes out from the reaction mixture, has got the trans E configuration concerning the carbon-carbon double bond, and S cis configuration concerning the sigma bond which link together the carbon-carbon and the carbon-carbon double bond carbon. Several modifications of Glaser-Schmidt condensation have been described in the literature. I've selected some which are successfully used in our laboratories as well to improve the yield or prevent formation of byproduct in the classical Glaser-Schmidt reaction conditions. One of them is the Glaser-Schmidt condensation reactions performed with microwave irradiation. As the mentioned literature describes, the yields, table 1, the yields obtained by means of microwave irradiation in practically all the examples means that the formation of byproducts is minimized. Another modification of the Glaser-Schmidt classical Glaser-Schmidt condensation using that perchloric acid treated silica gel. The perchloric acid treated silica gel as a very effective catalyst, and in the presence of catalyst, for example, pyridine, first item, piperidine, third, fourth item, sodium hydroxide. The yields are very well, even though the reactants are very complex carbonyl compounds. In some cases, as it's mentioned in the referred literature, the reactions are performed without using any solvent, which is definitely a great advantage of these synthetic methods. Another catalyst is which is reported in the literature, improving the yields is the protonated aluminate mesoporous silica material. Using this catalyst, particular aldehydes, special aldehydes and special carbonyls could be successfully condensed to form the respective chalcones. And you can see, using these catalysts, not only the E, whereas some cases the Z isomers are also formed. The formation of the E and the Z isomers is noticeable under particular conditions, which is important from that respect that the two isomers are relatively easy to separate under protected conditions. And as it's seen in the screen, the three-dimensional structure, and as a consequence of it, the reactivity and several physicochemical properties of the Z chalcones are very much different from the A from their E isomers. A relatively new but very efficient synthesis method is the Suzuki-Miyauga coupling reaction, in which boronic acid derivatives are used with palladium catalyst in aprotic solvents. Several successful synthetic application have been described with fairly good yields, as it mentioned in the selected examples. The carbon-relative Heck coupling reaction is also a reaction can be successfully applied in particular conditions. It's a three-component coupling reaction in which, by means of selection of the proper reactants, different derivatives can be obtained. And as we can see, in case of vinyl derivatives, third item, the products are the expected chalcone compounds. In some cases, literature describes application of boron trifluoride in form of boron trifluoride iterate as a catalyst of Gleisenschmidt condensation, and this is also the method of choice under which we have to protect the sensitive hydroxide substituents, which are sensitive to the basic conditions. A new approach and a new synthetic strategy of chalcone synthesis are the synthesis of the alpha substituted chalcone derivatives. The alpha substituents in the chalcone unit structure can several affect that modifies the three-dimensional structure, the polarity of the enone moiety, and as a consequence, as a final consequence, the degree of conjugation across the chalcone molecules. Several different methods, approaches has been described, which are summarized in this slide. And these methods are flexibly can be flexibly changed according to the sensitivity of the substituents of the carbonyl units, carbonyl reactants. As I mentioned before, Z chalcones has got different characteristics, physicochemical and physicochemical characteristics and chemical reactivity. So in some cases, the aim of the chalcone synthesis is to obtain Z chalcones in pure form. As it mentioned, as it's shown in the slide, the E and the Z isomer of chalcones are interconvertible. So the most common experimental conditions of conversion of E to Z isomers is illumination of the E isomers by light, and the E isomers are easily isomerized to the E ones by acid catalysis. That's why the synthesis of the Z isomers needs special conditions, and Yoshizawa and their co-workers, for example, described a method starting from siloxypropene and resulting in a cis chalcone, I mean the Zia chalcones concerning the carbon-carbon double bond. Another approach of chalcone synthesis is synthesis is the conformationally restricted chalcones. Chalcones are, as I mentioned, conjugated systems. However, they do have some small conformational mobility. If our aim, however, to synthesize conformationally restricted chalcones, as it mentioned in this example, we can synthesize chalcone analogs in which the stereochemistry of the chalcone moiety is very much different from those which are present in the conformational equilibrium of the open chain chalcones. This structural and conformational and differences makes the compound reactivity, biological activity different from those of the open chain ones with the previously mentioned configurations. Referring to the configuration of the chalcones, natural chalcones and synthetic chalcones, here are two examples describing these differences and describing the method by which we can distinguish the two different configurations. As it mentioned before, the most stable, the thermodynamically more stable configuration of the chalcones, of the natural and synthetic chalcones, have E configuration concerning the carbon-carbon double bond and S-cis configuration concerning the sigma bond. In some cases, however, the S-trans configuration is preferred, and those non-covalent interactions which can stabilize this configuration is widely discussed in the literature. As for our own works, our works are mainly concentrates on rigid cyclic chalcone analogs represented in this case. Our work are originally started from open chain chalcones. Afterwards, in the next step, we synthesized cyclic analogs of the open chain structure with different ring size. In particular, modifying the open chain chalcone and introducing a 5-membered ring, series number 2, 6-membered ring, series number 3, or 7-membered ring, series number 4. And then in the next stage of our synthetic work, we also synthesized and investigated reactivity and biological activity of the heterocyclic analogs of the series 3 tetralone derivatives, in which the carbocyclic, in which an oxygen atom or a sulfur atom was introduced into the carbocyclic unit of the molecule. Furthermore, We also synthesized the ferrocene analogs of this cyclic compounds, taking into consideration that some of the ferrocene analogs of known biologically, pharmacologically active compounds also showed very useful pharmacological effects. The stereochemistry of the cyclic analogs were definite. The isolated cyclic chalcone analogs were always had always E configuration. We investigated the EZ isomerism of these cyclic chalcone analogs as well, and we have developed gas chromatographic, thin layer chromatographic, and high pressure liquid chromatographic methods to separate the respective E and Z isomers for further studies, and to investigate how the ring size and how the substitution of the benzylidene unit of the chalcone moiety affects the rate of the isomerization and the equilibrium composition of the EZ mixture. Another important feature of any biologically active compounds are their lipophilic character. Lipophilicity is a very important physicochemical property of any foreign compound concerning the transfer of the compounds through the membranes, binding the compounds to proteins, the target proteins, and so on. What we observed was as follows. We developed the isocratic HPLC method, which qualitatively characterized the relative lipophilic character of the E and the Z isomers. The isomers, dichloromethane solution was irradiated, illuminated by laboratory scattered light, and it reached the equilibrium, and the Z isomers were isolated, structurally characterized by several analytical methods, and after the structural characterization of the Z isomers, we could investigate how the relative lipophilic character, the E and the Z isomers, are changing. In the first series, in which the ring size is 5, I mean the derivatives have got 5-membered rings. We simply call them Indanon derivatives. We can see the upper panel that the E isomer is more polar than the Z one, or in other words, the Z isomer is more apolar than the E one. If we change the ring size, increase the ring size from 5 to 6, the tetralone, in case of the tetralone derivatives, what we observe that the relative lipophilic character of the E and the Z isomers became much closer to each other, and the relative order of the lipophilicity of the isomers changed. Namely, in this series, the Z isomers were a little bit more polar than the initial E ones. If we further increased the ring size and we compare the relative lipophilicity of the 7-membered analogs, the benzosuberones, we could see that the Z isomers became much polar than the E1. What we can conclude from this series of experiments, that by changing the ring size of the chalcone analogs and modifying the configuration, the relative polarity, and which can be numerically characterized by the log p value, can be firmly tuned according to the need. The goal we wish to reach in order to improve their biological availability. Here is another series of results of another series of experiments, which shows the relative lipophilicity of several benzosuberon 7-membered ring chalcone analogs, comparing the lipophilicity of the differently substituted derivatives. What we can see that changing the substituent can also modify the lipophilic character of the derivatives as we expected, and the Z isomers, as it's shown in this in the graph, is generally lower by 0.65 log P units, which were determined by thin layer chromatographic validated thin layer chromatographic method. In cooperation with Brazilian authors, several other so-called hybrid chalcones were synthesized, carrying sulfonamide functional groups, and after the compounds were synthesized and structurally characterized, we were able to compare the difference of biological activity, some selected reactivity of the open chain sulfonamide chalcones and the ring formed derivatives with the quinoline ring system. Another structural modification which resulted in different biological actions and different reactivity was as a result of modifying the A ring, in which the so-called alkyl methylene derivatives, Mannich derivatives of the compounds were formed. This structural modification changed the lipophilic character of the starting derivatives, and as it will be shown in further part of the lectures, not only the lipophilicity, however the reactivity has also changed of the compounds, and the bioavailability of the compounds were also determined and investigated how the Mannich derivatization changed the bioavailability of the gastrointestinal bioavailability of the the chalcones and their mannich derivatives. The synthesis of these mannich derivatives were managed through using the social Aschen-Moser salt, and this Aschen-Moser salt is a very common reagent to introduce dialkylamino methylene units, not only to aromatic phenols, however, for label activated alkyl methylene derivatives as well, as it's mentioned in the literature. Briefly, that was the essential of synthesis of these compounds, the most important feature of their stereochemistry, and some aspect, for example, the lipophilic character, which are affected by the modification of the substituent and modification of the open chain structure by means of synthesis of rigid cyclic analogs of them. Thank you very much for your attention.
Thank you, Professor. Thank you, Professor. Agora nós vamos ter uns 15 minutos de parada para descanso de 15 minutos e a continuação a outra parte do nosso mini curso de hoje, que vai tratar sobre about the second part. The second part is about the second part, the other.
Oh, anti-cancer.
It's from anti-cancer use of the chalcones. Sobre el uso de chalcones como anti-cáncer, que han sido testadas y bueno, próximo en 15 minutos estamos de vuelta. ¿Ok?